Hello, everybody. Welcome back. Today we're going to be looking at Unit 5.2, which is going to introduce you to something called a rate law. So let's get started. So what you're going to learn how to do in this lesson today is how to write what is called a rate law. Okay, and the first thing that we have to remember is that chemical reactions are reversible. Okay, typically we think of reactions as always reactants converting into products, but it's important for you to remember that products can convert back into reactants. And as products accumulate, they're going to turn back into reactants, and eventually when the rate in the forward direction is equal to the rate in the reverse direction, that is equilibrium by definition. What we are going to be concerned with, however, is before equilibrium is established. We are going to be looking at rates, the speeds of reaction, right at the moment they begin. And at the moment that a chemical reaction begins, the rate is only going to depend on the amount of product there, because at time zero, we won't have created any product yet. So we're going to be looking at reactants only. We're going to be taking speed measurements as soon as the reactants are mixed. And this process that I'm going to teach you today is something called the initial rate method. So what I want to show you is an example of what a rate law looks like. So we have a balanced equation here, and what's written here in the middle of a screen is what a rate law looks like. You literally have the word rate equals, and then this lowercase k is something called a rate constant. Then you have a set of brackets. Remember, brackets mean concentrations, molarities, right? And they each reactant is raised to the power of some exponent. This little m and little n, these are called rate orders. Okay, and we're going to learn about how do you find what those exponents should be. Before we get into that, though, there's just a little bit of just important concepts to make sure that you've got. We touched on this a little bit just a second ago. When you are writing a rate law, you will notice from the previous slide that I included the reactants only. Okay, I do not have the concentration of the products, and the reason is we are looking at the overall rate at the moment that the reaction begins. At the moment that a chemical reaction begins, we have not created any product yet. So the products do not show up in a rate law, just the reactants. And as I said, our job is going to be to find the value of those exponents. And the way that you do that is by looking at experimental data. You can't get the value for those exponents just by looking at the balanced equation. Now, before we get into this, okay, just a little bit of vocabulary. There are two types of rate laws out there. And as I told you guys before, those of you that are familiar with calculus, you're going to see some words that are going to bring to mind some connections in calculus. I'm not going to make those connections, but again, there is some overlap here. The first type of rate law that we're going to learn how to come up with is called a differential rate law. Okay, which often in an AP question is often just called the rate law. If a question ever says determine the rate law, they mean this kind, a differential rate law. Later on in the unit, we're going to see something called an integrated rate law, And that is another subunit, which we will talk about later. But again, you see some of these terms you see in calculus, differential, integration, things like that. Okay, so as I said, we're going to be looking at the speed of the reaction at the moment that the reaction begins. That's why it says initial rate. And how we're going to figure out what this rate law is going to look like is by looking at experimental data like this. Okay, so I'm going to work through this question with you and kind of talk through it. We have a balanced equation at the top of the screen, and we are given experimental data. 3 experiments, and let's look what's in the table. We have molarities of the reactants. Remember, we're looking at the initial rate, so products have not been made yet. We're going to ignore products. And then the column on the right gives us initial rate speeds for each of those experiments. And it says determine the rate law. All right, let me get to a fresh screen here. And if you will recall, guys, a rate law looks like this. If this is the reaction that I'm looking at, we had ammonium as one of our reactants and nitrite as our other. And our job, ladies and gentlemen, is to find exponents x and y. And how do we do that? Well, we're going to find each one individually. Let's focus on ammonium first. Let me come back to the problem. What you want to do is you want to compare 2 experiments where the reactant you're focused on, so in this case ammonium, 2 experiments where ammonium's molarity is changing, but the other reactant or reactants, if there was more than 2, are remaining constant. So let me say that again. I'm going to look at find 2 experiments where ammonium is changing, but nitrite is remaining constant. Whoops. And that looks to me like I should be comparing experiment 2 and 3. And what I'm going to do is I'm going to write out the rate law using data from experiments 2 and 3. Okay, so let me go back to that previous page where I was. Okay, and watch what I'm going to do. I'm going to write, this is the rate from experiment 3. Rate equals K times the molarity of ammonium in experiment 3 was 0.200, and that's raised to the x power. I don't know what that exponent is yet. And the nitrite molarity was 0.010. I don't know what that exponent is either. And I'm going to draw a line under it. So that is all the information from experiment 3. I'm going to write the same placeholders, but from experiment 2, because those were the 2 experiments that I was going to compare. The molarity for ammonium is 0.100, again, raised to the x power, but I don't know what x is. And this was 0.010. And here's the deal, guys. This is essentially a gigantic fraction. Think about a fraction. When you have something that is the same in the numerator and denominator, you can cancel it out. So I can cancel out K, and I can get rid of that entire term as well. And here's how this simplifies. 5.40 divided by 2.70 is the number 2. And this whole big fraction simplifies down to this, 2 to the x power. 2 equals 2 to the x. So what is that exponent? It's a 1. Okay, so now let me come back up to the top of the slide here. I know now that ammonium has an exponent of 1. And if you wanted to, you could just, since it's an exponent of 1, you could just leave it as like that. Okay, so maybe it's easier if I write it like this. So this whole division right there, that equals 2. And this whole division is 2 to the x. Just I make sure that that's clear on how I did that. So x must be 1. And the good news, guys, is that these exponents are always going to be whole numbers. Okay, so let me erase that so I have a little bit more room. Okay, so I know my first exponent. Let's go back to the slide. Let's now find the exponent for nitrite. Now remember, whichever reactant you're focused on, nitrite in this case, I want to find 2 experiments where nitrite's molarity is changing, but ammonium is staying constant. So that to me looks like I should compare experiments 1 and 2. All right, so I'm going to go through the same process. Let me get back to that slide where I was. And we're going to do this process so we can find the exponent y. Okay, so I'm going to plug in. This is the rate from experiment 2. Rate equals K times. This is the molarity of ammonium. And now I know that ammonium has an exponent of 1, so I don't have to write a variable for its exponent. 0.010. Now this one is still a variable because I don't know what that exponent is. I'm going to draw a line. And here is the rate from experiment 1. Okay. And the molarity from ammonium raised to the first power. 0050 raised to the power of y. Okay, and 2.70 times 10 to the negative 7th divided by 6.75 times 10 to the negative 8th, that is 4. This cancels out, this cancels out, this cancels out, this cancels out, and I get 2 to the y. So what does that exponent equal? It equals a 2. So I'm going to come back up to the top. And now, ladies and gentlemen, there is my rate law. So I had to go through this process of like dividing the 2 lines in order to find each exponent. Okay, so that is the thought process on how you find the exponents, or what it's called the rate orders. So according to our final answer here, ammonium is a first order reactant and nitrite is a second order reactant. Okay, so that's what's called the initial rate method. If you are ever asked not just what order is each individual reactant, like ammonium was a first order reactant, but what if you are asked what is the overall reaction order? That's real easy, guys. Let's say this is your rate law. All you have to do is add up the exponents. So that first reactant has an exponent of 1, H2 has an exponent of 2, and so on. Add them together, we would say this reaction is an overall 6th order reactant. So here's what I'd like for you to do. You're given another table of data that looks very similar, different reaction though. What I want you to do is use the method that we just did to come up with the rate law, meaning I'm asking you to solve for those exponents, solve for the orders of each individual reactant. It also asks you to find the overall reaction order. And then the last question, it says, what is the value of the rate constant? If you think you know how to do it, go ahead and try it. Otherwise, I'll talk that part out with you. So pause the video, solve for the rate law and the overall reaction order. All right, let's see how you did with the first part of this problem. So to find the exponent, the order for nitrogen monoxide, I compared lines 2 and 3. The second part of the problem here, to find the exponent for chlorine, I compared lines 1 and 2. I used this initial rate method. I found nitrogen monoxide to be a second order reactant and chlorine to be a first order reactant, and overall I added my exponents together. It's a third order reaction. By the way, if you're wondering, what does it even mean to be a certain order? Okay, remember what we talked about in the first lesson in this unit. The higher the order, okay, the faster that reactant is being consumed, okay? So since I have now determined that nitrogen monoxide is a second order reactant and chlorine is only a first order reactant, nitrogen monoxide is being consumed, used up faster than chlorine. The higher the exponent, the faster that reactant is being consumed. Okay, now, the last part of this question said, determine the value of the rate constant. And what you're going to do is choose any one of the experimental lines from the chart. It doesn't matter which one. I usually just pick the first line because that's just my habit. And I'm going to switch to a fresh screen here. Okay, so here was that rate law again. Nitrogen monoxide was second order and chlorine was first order. I'm going to pick the data from line number 1 and I'm literally just going to plug it in into its positions. So the rate on line number 1 was 0.18 molarity per second. I don't know what the rate constant is. That's what we're going to find. That's the molarity for nitrogen monoxide. Let's make sure to square it. And this is the molarity for chlorine. Go through, you do the math, and this is what the rate constant comes out to equal. Now here's the tricky part, okay? The question usually is going to say determine the value of the rate constant with appropriate units. And ladies and gentlemen, I hate to say this, the units for K, that rate constant, are different for every question. But I'm going to show you how to figure it out. Okay, I'm going to take this rate law and I'm going to bring it down here. And instead of plugging in values, I'm going to write the units that go for each entity within that rate law. For example, rate is in units of molarity per second. I don't know what the units are for K, so I'm going to leave that as a variable. Brackets mean molarity, and this molarity is squared, and this molarity is just to the first power. Okay? And I'm just going to simplify this a little. This is molarity to the third power. If I am trying to find the units for K, think just simple algebra. I need to isolate K. Okay, this cancels out. And think, again, think algebra. How can I simplify this fraction on the left? I can cancel this out and this becomes a 2. Now this looks really messy right now, but I'm going to clean it up. There's many ways you can write the units in this problem. I'm going to write them in multiple ways. All of these are acceptable. I could write the units like this. Molarity to the negative 2 power, because that molarity squared is in the denominator. And so is seconds. That's also in the denominator. So it's molarity to the negative 2 times seconds to the minus 1. You could write that. You could write this, 180 molarity to the negative 2 per second. I could write that. Or it's not as pretty, but it works. All of those are the same thing, and they're all acceptable. But can you guys see why I said the units are different for every question? Depending on what the exponents are in these positions, the units are going to be different. Okay? Now there is a little bit of a trick, but I don't want you to memorize this. I want you to, understand the math here. Okay? This reaction was overall third order. Okay, we said that on the previous slide. Well, guess what, guys? The units for K are always going to be molarity to the negative and one number less than the overall reaction order. Like the overall was third order. So the units are always going to be molarity to the negative, one number less per unit time, which is usually going to be seconds. So you can memorize that pattern if you want, but I prefer that you just be able to work it out algebraically. Okay. So to make sure you have got this, I want you to try one more question on your own, completely on your own. I want you to pause the video and try it. I want you to find the rate law, the overall reaction order, the value of the rate constant, and its appropriate units. Go. All right, let's see how you did. So using that initial rate method, this is what you should have gotten for the rate law, which I've boxed in red at the top of the slide here, which shows us that X is a second order reactant, Y is a first order reactant, which tells us that the overall reaction order is a third order reaction. I just picked the first line of data to plug into that rate law, and I solved for K. If you chose a different line than I did, would you get a different value for K? Maybe slightly, but they should be pretty close. But it doesn't matter which line of data you pick. I picked the first line, and there are my appropriate units. So that is what's called the initial rate method. So that was something that is new. We typically don't cover the topic of kinetics and rate laws and all that in Chem 1. So this was likely something that was completely new to most of you. But I hope that you feel a little bit more comfortable with it. I hope you learned a little something, and I look forward to seeing you next time.